Hey everyone, welcome back. So in this video, we shall continue looking at or studying the normal distribution. So we have yet to investigate the mean and the variance of the distribution, right? So we will do that in this video. But before we can do that, we need to study these two concepts. So first is that of an odd function. So h is an odd function if h of minus x is equal to minus of h of x. So for example, if we take h of x is equal to x cubed, then we know that minus x cubed is equal to minus of x cubed, right? This relationship holds. That is, h of minus x is minus of h of x. So therefore, this is an odd function. And we also have a concept of even function where g of minus x is equal to g of x. So for example, x raised to 4 is an example of an even function, or even x squared, right? So minus of x squared is equal to just x squared, right? These are the same. So therefore, this is an even function, and you see that even function is looks like this. It's symmetric. So these odd and even functions have certain properties, and we shall use these properties to calculate the mean and the variance of the normal distribution. So for odd function, this integration, right? This integration, so the limits of this integrals have to be symmetric. So if it's minus infinity, the upper limit has to be plus infinity, h of x dx, and this integral is going to be 0. In fact, if I integrate this over minus a to a, where a is some number, h of x dx is also going to be equal to 0. Okay, so let's understand a little bit why this is true. Okay, in fact, this is true even if h takes discrete values, right? Or even if x takes discrete values. So for example, instead of summation, if I have h of x, right, and x takes values say from minus a to plus a, or minus infinity to infinity even, this sum is going to be equal to 0. So let's maybe look at an example to understand this. Right, so say h of x is equal to minus x. This is the function, and x takes values plus minus 1, plus minus 2, and 0, right? So from minus 2 all the way to plus 2. So let's see what h of x, right, where x goes from minus 2 to 2 looks like, right? So we have h of minus 2 plus h of minus 1 plus h of 0 plus h of 1 plus h of 2, right? This is what we have. But we know that h of minus 2 is just equals to minus h of 2, right? Because or I can even write it this way, right? So h of x is equal to minus of x. So therefore h of 1 is equal to it's an odd function, so h of x is equal to minus of h of minus x is minus of h of x, right? We know that this condition holds true because this is an odd function. So therefore h of minus 2 is minus of h of 2, right? And h of minus 1 is minus h of 1, and so on. So therefore this expression, you can write it as minus h of 2. So h of minus 1 will be minus h of 1. At 0 it is 0, and h of 1 and h of 2, so all of these cancel out, right? So this function, so this is an example of an odd function, and you can see if you take a summation, values kind of all cancel out, and similar property holds true even for the summation, right? In fact, for the summation, you can actually show, say if you're integrating from minus a to a, h of x dx, you can show that this is equal to 0. So you would split this integral into two parts, right? Minus a to 0 h of x dx plus 0 to a h of x dx. And now I'm going to call this as 1. And now minus a to 0, that's the first term here, can be written as, so we can make a substitution, right? So we can substitute u is equal to minus x. So if, so with the substitution, this integral becomes, so if x is minus a, u is a, and 0, h of x is minus u, and therefore du is minus dx, so dx is minus of du, right? And we know now h is an odd function, so I can write this as a to 0 minus of h of u du. This minus minus cancel out, become plus, right? And remember, this u is just a dummy variable, right? I can replace u with x as well. So x dx a to 0. But now I can change these limits or reverse the limits. It's going to be minus 0 to a h of x dx. Okay. So this first term here, right, is just minus of this term, right? And therefore this term and this term cancel out and you get 0. Okay. So we just also saw some revision as to how to do some change of variables, right? So this integral can be split into these two parts, and similarly if you have infinity you can still do the same thing. So we work with the first interval, we do change of variables, we use the fact that it is an odd function, and then we reverse these, or we interchange these limits, so therefore you have this minus sign again. And finally this plus this, so this is the same as this term, so this term plus this term, they cancel out and you get a 0. So that's why integral of over odd function is 0. So for even function, you can show that this integral is 2 times this integral. So again, you can use similar techniques that I have shown you. You can use this change of variable to show this. So it's a good idea to go ahead and see that if you're able to prove this. Okay, so I'm not going to do that here, but it follows pretty much on the same line as this result. So next we look at the mean and variance calculation. So if x is normally distributed, then the expected value is just the first so the expected value is this first parameter mu, and variance is the second parameter sigma square. So there is a reason why we denoted the two parameters of normal by mu and sigma square, right? We could have called them a, b, or any other letters, but we usually reserve mu for the mean and sigma for the variance or the standard deviation. So there's a reason why the two parameters are named this way, because the first one happens to be the mean and the second one happens to be the variance. So let's show this. So the expected value of x is the integral over t f of t dt, where f is the density of a normal distribution, right? So this is the density, f of t is this, right? This is the density of a normal distribution. Then we do a change of variable, so we make a substitution. That's t minus mu by sigma. I'm going to call it as y, and with that I'll get t is equal to sigma y plus mu, right? So this will give us t is equal to sigma y plus mu, and this also gives you dt is equal to sigma dy, right? Mu is a constant. And if t goes from minus infinity to infinity, y also has the same limits. Okay, so the limits still remain from minus infinity to infinity. We make the substitutions, and this is the integral in terms of the new variable y. Now I have mu plus y times sigma y divided by this times this. So we split this into two parts, right? So first part is, so this is the first part and this is the second part, right? We're splitting this sum into two parts. We're opening it up. So now if you observe this, this is nothing but the density of a standard normal variable. What is a standard normal variable? Where mu is 0 and the second parameter is 1, right? So remember 1 upon sigma square root of 2 pi e to the power minus 1 by 2 sigma square y minus mu whole square, right? This is the density of a variable with mu and sigma. Plug in mu is equal to 0, sigma is equal to 1. You get 1 upon 2 pi, 1 upon 2 y square. So what we see here is a density of a standard normal variable. We know because it's a density that it integrates to 1, right? So therefore this integral is 1. We haven't proved yet that this density integrates to 1, but you know that it's a density, therefore it has to integrate to 1, right? We haven't verified it though. However, this first integral is just 1, so you're left with mu. And this here is an odd function. And this is an odd function, and you're integrating from minus infinity to infinity. Therefore, this is 0. So you see how knowing this trick about odd and even function helps you solve this relatively complicated integral. So the expected value is just mu. So next we look at variance of x. If you remember the definition of the variance of x is expectation of x minus mu square, right? So this is the so we'll be using this definition. So expected value of this, so integral t minus mu square times the density, right? This is just the definition of expectation. Then in this step I've substituted the formula for the density. Then we make a substitution. Y is t minus mu by sigma. With this you need to change the variables appropriately again, right? So t minus mu is y sigma, so t minus mu squared is y sigma whole square. So that's here. T minus mu by sigma is just y square, so you have this y square here. Okay, so you're just making the substitutions. Then you pull out all of the constants, and this is what you're left with. But now this also this here is an even function. Okay, so all of these are constants, and then you can ignore those. So y squared e raised to minus y squared by 2 is an even function. Therefore this whole integral is 2 times integral from 0 to infinity times this, integral of this. Okay, so this is an even function. Therefore this integral is now from 0 to infinity, and you have this 2 here. So once we do this, then it is time to use those results about the gamma function that we saw last time. Okay, so if you open back those results, you will see that this term here has this formula. Okay, so you really need to know the results about the gamma functions. So once we do that, then we are almost done, right? Then all of these terms, you need to be a bit careful. These terms cancel out, and you'll be left with sigma square. So just to make better sense of this, let's just look at the gamma function quickly. So this is the result we'll be using, right? So what we have here is we have y square e to the power minus y square by 2. So we have two results, and here it's e to the power minus ax, and here we have ax squared. So we have the square term here, right? And we have this y square here. So we'll be using the second result, right? So let's compare this term with this term, right? So e raised to minus a times x square. So here y square is multiplied by half, so a is equal to half, and x raised to b minus 1, so y raised to 2, so 2 can be written as 3 minus 1, right? So b is equal to 3. So therefore this is gamma 3 by 2 times a raised to 3 by 2, right? A is half and b is 3. So this is what we get. And now if we simplify this, right, let's just quickly see how to simplify this. Also remember that gamma of half is square root of pi, right? Because we have this pi here and this needs to disappear to get sigma square. So let's see how to simplify this, right? This is what we have currently. So 2 and square root 2 cancel, right? So what we have is square root of 2 in the numerator, sigma square, square root of pi. This is gamma 3 by 2. Remember, gamma n can be written as n minus 1 times gamma n minus 1. So 3 by 2 minus 1 is just half. So the numerator can be written as half times gamma half divided by 2 times. So half raised to 3 by 2. 3 by 2 can be written as 1 plus half. So it's half raised to 1 plus half. So which is half raised to 1 plus half. Again, remember gamma half is square root of pi, right? Not this one. So if you go back to the results here, gamma half is square root of pi. So that cancels out. Then we have this square root here, this half here, we have this 2 in the denominator. Of course, we have the sigma square. This half can be written as half times half raised to half, right? And so now this cancels, this cancels. What we have is 2 sigma square, 2 times 1 upon 2 raised to half, which is square root of 2, square root of 2 sigma square. This will cancel out to give square root of 2 here, and this cancels out to give sigma square. I mean, there are different ways to simplify this, but I just wanted to walk you through the details of this. All right. So thus we can show that variance of x is sigma square, right? So that's all for this video. I will see you in the next one. Thank you.